it's time to get started, so I guess we should go ahead and get cracking. We are starting chapter three. I want to remind you guys that Sunday, uh, anytime after 12:00 and 1 second a.m. on Sunday, June 7th, you can start your test, your first face-to-face, quote unquote, face-to-face test, but you have to have it finished, of course, before 11:59 and 59 seconds p.m. on Sunday, June 7th. Or actually, for you guys meet on Tuesdays and Thursdays. No, yeah, I did do the 7th for y'all. So I just want to remind you that your test is due on that day, and you have to take it on that day. You've got to find some time in your day, in that day, to fit in that test. You will be allowed. I think I gave you a 90 or 100 minutes, something like that. That should be more than enough time. I might even give you more time than that. The main thing is you have to use Respondus Lockdown Browser. You have to use Respondus Monitor. Of course, if you're using Respondus Monitor, that means you have to have a webcam. Also, you have to have a reliable internet connection. You have to have a reliable browser that can run Canvas, Canvas Quiz, Respondus Lockdown Browser, Respondus Monitor, and can work a webcam. And of course, you're going to have to be tested with that running. So there's a camera going to be on. You're going to have to pan the camera around the room, show me all the places that are within lungeable distance from you. So, for instance, if you're working at a desk, you'll have to take your, if it's the camera's actually mounted on your computer monitor, for instance, you'll have to take the camera and bring the monitor and bring it out here and show me your feet area, your whole desktop area, everywhere you can reach, so over there, and you'll have to pan around the whole room like this, showing me that you're in an empty room with no other students. The door should be closed. It should remain closed the whole time. Uh, we won't necessarily need you to speak, but we do sort of need to be able to hear the room to some extent. Also, you need to be very careful if the computer flags you as being suspicious, then I'm going to assume you are suspicious. So if you're doing a lot of this, that's a good indicator. You know, if you're looking down too far, that doesn't mean you can't look down. You should be looking down. But if I look and see you looking down at a page on your desktop working surface, that's fine. But if I see you looking into your lap or something like that, that's going to be suspicious. And first time, what happens is basically that test will be ended. You won't get that grade. You'll have to reschedule or something like that. So just don't do that. Okay, just try to be on the up and up as much as possible. And basically what we're going to do is there will be a part that might be multiple choice, but the vast majority of it's just going to be what I'd call short answer or essay or something like that, where you're going to solve problems. But in order to solve those problems, you have to show me the work. You have to show me your final answer. You have to write the work neatly, top to bottom, left to right. None of this, working in circles and stuff like that. That doesn't work for me. I can't have problem one and then somewhere in the middle of problem three is number seven or something like that. It really needs to be problem one, a line, box around the answer or answers, then problem two, a line finishing that work, answers, boxes or circles around the final answer, so on and so forth. You have to show me work with everything, even if you get the right answer. If you get the right answer, that doesn't necessarily mean you'll get more than half credit for the actual problem. So even if you have exactly the right answer that I was expecting, if you show no work, you're at best going to get 50%. Okay, so keep that in mind. Again, that's going to happen on June 7th. That's what I mean by face-to-face tests. Now, you will have, like I said, Respondus Lockdown Browser, so you can't surf the web for other things. You'll have to show me everything on your surface of your desktop. Any papers you bring, which of course could be your equation sheet, could be your important facts, all of those will be in the test, because the way you'll pull up the test is the test will be quote unquote looking like an online test. There will be a test that you click on and it'll have questions. And at the bottom of that test, we'll have the answer, the equation sheet, as well as all the information that you might need, tables, conversion factors, constants, all that stuff will be there, SI prefixes, basically all the stuff you see in the important documents and links that I told you about, test accoutrements or whatever. They'll all be available to you. Uh, in addition to that, you need to make sure you show me your work. And as I've been telling you so far this semester, when you show me your work, what you want to do is as you're writing, as you go to solve a particular problem, you want to write down a variable for each of the quantities they gave you. Specifically, like if they give you an initial speed, you want to write v sub 0 equals, and then you write down that speed with its units. In other words, it's not only about writing down what you know, it's assigning it the appropriate symbol. So if you put down, for instance, x is equal to 3.2 meters per second, then that's not going to make any sense, and I can't give you any partial credit for that. So you're going to basically take all the information that they imply or tell you outright, and you're going to assign it a symbol or variable that's consistent with what you've been learning in the course. So, distances or positions are represented by x. Distances might be d as in displacement, or it could be x or delta x, something like that. V is a velocity, v sub 0 or v sub I is initial velocity, v or v final or V1 can also be considered a final velocity. Those are all three symbols for final velocities. A is an acceleration, that kind of stuff. Theta is an angle, phi is an angle, alpha is often an angle, all of those things. And then once you've written down everything that the question gave you with the appropriate symbol, you're going to write down the appropriate symbol for the answers that they want. So if they're asking you, for instance, for the acceleration, you'll say A equals question mark. And I want to see that A equals question mark. Or if there's multiple ones, then I want to see A equals question mark and V final equals question mark. And then you should start by writing the equation or equations plural that you will use in solving that problem. So you could write down multiple ones, and then when you're finished solving it, you realize, oh, I only used two of those. Well, erase that third one that you put and the fourth one or whatever that you put. Either erase it or just draw a line through it so that I see you only gave me the two equations that you really did use. And then one more step as part of your work, you want to show it taking that equation in the unadulterated form, the form that it appears on the equation sheet. You can you need to show it that way initially, but then when you go to plug in numbers, you can solve that equation first for any particular variable and then plug in the numbers, or you can plug the numbers in that unadulterated form with their units as well. But the main thing is I want to see your equations. I want to see them as they're originally shown on the equation sheet. And then I want to see some form of that equation with the values put into it with their units. After they're shown once with those units, you don't have to keep up with it anymore. However, it's usually good for you to. I just need to see that initially because then I can give you copious amounts of partial credit for the test. So hopefully that gives you a better understanding. There will be instructions on it to tell you some of this, but it's more important that you hear it now than in the stress of a test trying to read it. So make sure you have that done. So remember, sometime during Sunday, you have to get your test done. And like I said, I'm going to give you at least 90 or 100 minutes. I'll probably even give you more because normally the face-to-face tests will occur during your lab meeting. And you guys actually have a face-to-face lab meeting. So Dr. Johnson could, for instance, give you his exam or could actually orchestrate the exam in his lab on, I think it's Thursdays, or actually I'll meet Tuesdays and Thursdays. So whichever day we do it in the future tests, they'll be on that. Mr. Johnson will let you know what his plans are for your lab day this coming week. I've given him a bunch of options. He has a bunch of options that he might consider as well. So before we get started, does anybody have any questions either on the material or the test or anything like that? Several people have logged in while I was talking. Just want to remind you to chat me your first and last name if you haven't done so already. But I'm opening up the floor again to questions about anything. The course material, the problems that you're having problems with, practice test questions, uh, protocols on the test, all that good stuff. Anything?
Hello. My name is Shania Brown.
Yes.
So I emailed you. I was having trouble finding the Zooms and stuff. I finally found it.
Yes.
And so you said I know the test is on Sunday. I won't even be in town, so I'll be in a hotel with my family on
hmm
Sunday. So I don't know. I won't be able to be. I don't want the test to just shut off because I won't be in a room where I can just be the only one in the room.
Uh, mm, There might be, well, you have to talk to me after class. There's a very
Okay.
specific process that we'd have to go through. Normally, you're not allowed an alternative test time for these online face-to-face tests because I have to make up a whole different exam if everybody doesn't take it at the same time. So taking it on the same day is normally what's going on. But I'll check
I didn't
your.
think a test would be on a Sunday. That's all. And like
Yeah,
I'm
yeah,
going for the weekend, so I didn't
yeah.
think I was like, oh, a Sunday. I won't
I
even,
get you.
you know.
Yeah, yeah, and I know, and the only reason why I put it on a Sunday was because it was supposed to be on Wednesday. I just didn't feel it was fair to keep y'all to do that. Would you? I mean, if you want to prefer to take it on Sunday, I could do that for you. I mean, on a Thursday or whatever, I could do that for you. But I'll send you an email, and we might even communicate at that point via text message if that's more convenient for you. It's a little bit
Yes,
easier
that
for me.
works.
So I'll check that, and we'll communicate after class tonight
Okay,
and
thank
or
you.
tomorrow. But yeah, we'll work it out. Don't worry, it's not a big deal.
Thank you.
No problem. Anybody else? Okay, so yeah, just keep in mind I have the dates set on the syllabus, which we had some confusion with this first test, so it's no big deal in this scenario. But the remaining tests, remember, they have very specific dates, so let's try to knock those out on the times that they're prepared in the future. So I won't be holding them on weekends in the future, but you will have to do them some during some 24-hour period. So keep that up for the remainder of the semester in terms of your syllabus, and hopefully I won't have to make any more changes, so we won't do that. But I'm always going to be reasonable with you, and I'm always going to give you the benefit of the doubt and help you as much as I can because I'm very pro student, student centered type teacher, even though I do teach a quote unquote tough class. So let me know if anybody else has anything. Anybody have any other questions? All right. Well, I think we're going to go ahead and get started. I want to remind you that we're going into chapter three. Chapter three is called, actually, it's called kinematics in two or three dimensions. And then it says vectors. And our lecture tonight will be basically on vectors. So I've been hitting at vectors a little bit already. I specifically told you that scalars are quantities that are just numbers. Specifically, they're either a pure number or what we call a denominate number, denominate number. And that's just a number that has units. For instance, pi is generally considered a pure number. It's 3.14159, but it's a non-terminating, non-repeating decimal. And it generally doesn't have units. However, you can have things whose magnitude is pi, and then they would have the units of meters per second or something like that. In that case, it's no longer a pure number. In that case, it's what we call a denominate number. And if that number, if that word bothers you or makes you is a number you're not familiar with, a word you're not familiar with, just remember that the bills that you have, like a dollar bill, a $5 bill, a $10 bill, 20, those are called denominations. So hopefully that'll ring some bell to you when I say denominate numbers. But that's what a scalar is. And our archetypal example of a scalar is speed. And I say it's the archetype because both of them start with the letter S. But there's a lot of other ones. Energy is a scalar quantity. Pressure is usually a scalar quantity, but you could make up pressures that are vector quantities. Time is a scalar quantity, that kind of stuff. Drawing a blank on it. Oh, mass. That's another one. Then there's quantities called vector quantities, and vector starts with a V, and our archetypal vector is really not velocity, but I'm using velocity because velocity is a vector quantity, and it also starts with a V, so that's kind of helpful. Really, the archetype of a vector quantity is the displacement that we talked about in chapter 2. Remember, I said there you can imagine the displacement as if it's an arrow that points from where an object was to where an object ended up. So if an object's here and then ends up here, that object might have went some crazy path back and forth, and did all this crazy, and then ended up right here. If that's the case, then it doesn't matter all that stuff that happened. The displacement from A to B is just an arrow drawn from A to B. So it's an arrow here. The head of the arrow would be up here, and the tail of the arrow would be back here. That is our displacement vector. Okay. If you wanted to break that motion up into smaller and smaller portions of the trip, remember the trip went all like this and stuff. You could say the displacement is this little bit, and then 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 this little bit, and do all that, and you'd have like 1,000 of them between A and B. But the key point to understand about all this is the sum sum of those thousand is equal to the total one that I got. So for instance, when I went from A to B, that is the final vector that represents the displacement from position A to position B. And if you had instead broken that up into a little displacement from A to, let's say, C1, and then from C1 to C2, and then C2 to C3, C3 to C4, C4 to C5, so on and so forth, you'd have a bunch of little individual displacement vectors, C1 to C2, Cn to Cm, so on and so forth. And the last one would be Cn to B, right? If you added those individual displacement vectors, C1 to C2 plus C, or actually I should say A to C1 plus C1 to C2 plus C2 to C3 plus C3 to C4. If I added up all of those, that result would be the vector from A to B. That's what I mean by displacement is an archetype of vectors. So it gives us a sense of understanding of what we mean when we're talking about add vectors. Now that was all said in words, and hopefully you can follow it. But just in case you can't, let me show you it with word. I mean with drawings as well. So I'm going to go ahead and share my iPad screen with you all. And remember, even if this gets confusing and all that good stuff, you still want to ask me any questions in real time. Just speak right up. I usually don't notice whether or not you're doing the little hand up thing, so I don't necessarily see that, but I will try to keep an eye on it. But the main thing is, if you have a question, just speak up and let me know, or chat me, let me know, or do the little hand holding up thing that Zoom allows you to do. And you probably all know more about Zoom from that side than I do. I'm just used to it over here from the instructor side. I now have the chat window open as well, so I should be able to see that. Right now, you're looking at my Good Notes document, and I want to start off giving you some idea what I'm talking about with regards to displacement. So let's imagine we have our house. So let's say our house is this right here. Okay. And then on our house, we have a front porch, and then we have a first step, a second step, and a third step to get down to the sidewalk. And then we have a sidewalk that goes out here. And then, of course, we run into the sidewalk that runs along the road. So that sidewalk goes this way and this way. And then here's the other part of the sidewalk. And then here's the curb. And then this right here would be the road. And that's enough of what we're showing here. So what we could do to represent a vector so we'll have some understanding of it is I'm going to imagine that we start off right here just outside of the front door on the front porch, and that is position A. Now I'm going to draw with blue lines the path that I actually take. So let's say I walk like this, and then okay, let's say I've been drinking or something, so so I'm walking like a crazy person here and there, and I go like that, and I go over here and seem to find some dog poop. I try to check if see if I need to clean that up, and then I go over here, it looks like another pile there, and then I go like this, and then I walk over to here all of a sudden, and then finally I walk out to here, and let's call this position right here, let's call that B. Now, in principle, what you might have seen, and this is why I made these points, is this would be C1, this would be C2, and I mean that dot right there, that dot right there. This would be C3, this would be C4, this would be C5, this would be C6, this would be C7, this would be C8, this would be C9, this would be C10. And then, of course, C10 to B would be the last one. So what we could imagine is that there were several vectors, and specifically what I want you to understand is the displacement vector from A to B is this guy. That is the displacement vector from A to B. Okay. Now, the vector from A to C1 would be, for instance, if I zoomed in, it would look like this little bit right here. That's A to C1. And then C1 to C2 would be that little bit. And then C2 to C3 would be that little bit. C3 to C4 would be that one. C4 to C5 would be that one. C5 to C6 would be that one. C6 to C7 would be that one. C7 to C8 would be that one. Notice all the different ways I'm drawing the vector heads. That's C8 to C9. And then I have this vector over here, which would be C9 to C10. And then I could ultimately go from C10 to B. And each one of those are vectors. So notice that in this case, I drew a green vector from A to C1. That's the displacement. That represents the displacement from position A to position C1. There's also a vector from C1 to C2 that represents another vector. And there's another vector from C2 to C3 and C3 to C4 and C4 to C5 and C5 to C6. What I mean by all of this is that let's actually call this, I'm going to say that displacement vector from A to B, I'm going to call that vector D. So that's the name of the red vector from A to B. Okay. I'm going to say that AC1 plus C1, C2 plus C2, C3. Notice I'm using a double letter, double subscript symbol for the actual names of the vectors. That is a thing that we can do, and that is a thing that we occasionally do, but you don't necessarily need to. You normally just do it with a letter and with an arrow over top of it. So that's why I'm showing you the arrows. That's how we tell people, hey, this quantity I'm talking about is a vector, not a scalar. If it was a scalar, it would normally be, for one, oftentimes we use a lowercase letter, and two, we never put an arrow on top of it. Okay. But as you can see, the first little green vector was AC1. The second little green vector was C1, C2. The third was C2, C3. C3, C4 is the next. C4, C5 is the next. C5, C6 is the next. C6, C7 is the next. C7, C8 is the next. C9, or excuse me, C8, C9. I'm having a hard time remembering how to count, evidently. C9, C10 is the next. And then C10 to B is the final vector. And what I'm saying is that all is equal to vector D. Okay? So this gives us a prescriptive method of adding vectors, at least graphically. You can take a displacement and just remember a displacement is represented by an arrow because the arrow is a good representation of a vector. And the main factors for to make something a vector is that a vector is a quantity that has magnitude and direction, not unlike what they said on Despicable Me when the bad guy Vector was introducing himself. He said it's a mathematical term. It means a quantity that has both magnitude and direction, or something like that. So that was the actual real definition of vectors. And a vector is an object that has a magnitude and direction. So for instance, when you look at your speedometer, it tells you a certain number of miles per hour. okay, maybe 55 miles per hour, that is a denominate number, and it doesn't have anything about direction. It just has a magnitude. It has a quantity associated with it. So that number is in fact a scalar. But if you also have a compass heading reading in your car by either a compass mounted on your dash or maybe an electronic compass that reads the heading to your screen, like my wife's car, I noticed did, or actually, no, it was my car. Yeah, it was my wife's car. Had the other day. It actually had southeast and it had said south southeast, that sort of thing. When that happens, then you have what's called a velociometer, because the velocity is a vector quantity, and 55 miles per hour south southeast is specifically a vector quantity. It is a quantity that has magnitude 55 miles per hour and has a direction south southeast. Okay, technically south southeast means 22 and a half degrees south of southeast, and southeast means 45 degrees from south and 45 degrees from east. So south southeast means a little further to the south than southeast, and specifically it means halfway between southeast, which is 45 degrees, and south, which would be the full 90 degrees. So halfway between 45 and 90 is a 22 and a half above 45. So that would be what, 67.5 degrees? Uh, Basically 67.5 degrees from east towards south. Okay. So that's how we could specify a vector quantity. We have to give a magnitude, we have to give a direction. And what we've seen here is that evidently, if you draw the vectors head to tail, because notice here, this green vector right here, for instance, that green vector has its tail, which is this quantity, at the head of this vector. So this configuration right here is called head to tail. So when a vector and another vector are head to tail, they are said to be in head to tail position or head to tail configuration. And what we've learned from this archetype of displacement is that when you string up the vectors one after the other, head to tail, head to tail, head to tail, head to tail, you draw a single vector from the head of the first to the tail of the last, or excuse me, from the tail of the first to the head of the last, then that vector represents the sum of all the vectors. Now, it turns out if I, instead of putting C1, C2 at the head of AC1, I could put C2, C3 at the head of C1, and it turns out you're still going to get the right answer as long as you put the same vectors in there. So it turns out I could actually add these in any order I want. AC1 plus C1, C2 plus C2, C3 is ideal, but I could juggle them any way I wanted and would still get the same answer. And the reason behind all this is that stuff that you learned in pre-algebra that seemed kind of a little stupid sometimes and redundant, stupid things like A plus B is equal to B plus A. Duh, right? Well, you'll learn later on in higher levels of mathematics, there are numbers and quantities that we interact with that A plus B does not equal necessarily B plus A, are numbers that when you multiply A times B, you do not get the same thing as when you multiply B times A. Those are quantities that are going to come in the future, but right now it just seems stupid because, of course, they're that way. Well, that's all part of a bigger idea in mathematics of an algebra and what we call ultimately a vector space or an algebra space or a Lie algebra, these different terms. What we're getting at here is the idea of algebra that you know of from grade school and probably up through pre-calculus was that algebra was a series of tricks that you learned that you could do with symbols so that you could solve an equation for unknowns. And that's somewhat right, but there is an idea in mathematics that there is a thing that constitutes an algebra, and that algebra consists of definitions of operations and definitions of the space in which those things exist, and that as long as they obey those rules that we learned about that were so stupid, then they're considered a vector space and a vector algebra or something like that. And vectors are actually a more general case of the quantity that is a number. So numbers are a subset of vectors, and then vectors are a subset of tensors, and you might even consider matrices as a subset of tensors. And then there's bigger things, there's spinors and all sorts of crazy stuff that we interact with. But the main thing is that is why some of the same things we learned that seem so stupid in pre-algebra, we still use them today. And you're going to see that come up in a second when I start to teach you how to subtract vectors. Okay. So let me take from what I've just explained regarding this archetypal model of vectors. I'm going to define for you how we graphically add vectors. So first off, I'll say scalar is a pure number or a denominate number. And examples. The first one, of course, I'm going to put is speed. And it would have helped if I drew that S a little more S-like. But speed, I'm using that as my initial example just because it starts with a E. But another one is mass, uh, also energy, time. Those are all quantities that are represented by scalars. Then a vector is a quantity or object that has a magnitude, which we call a size, if you will, and a direction. And of course, there's other properties too. For instance, one of the ways we actually learn it in a higher level math is you just learn that a vector is a quantity that transforms when you switch coordinate systems in a very specific way. So if you go from one coordinate system to another, there's a multiplication process that you can do. And if that multiplication process matches this model form that they give you, then you know it's a vector. If it doesn't match that, then you know it's not a vector. But it turns out that that's equivalent to saying it has to have a magnitude and direction. Examples of this, again, I'm going to start with the one that's most helpful, which is the one that starts with a V. So that quantity is velocity. But our archetypal one is displacement, acceleration, and force, and momentum. And there's others. You haven't learned enough physics right now, unless you've had another physics course in the past. You probably haven't learned enough physics right now to specify a lot more. But one thing you can think of is if the quantity that you're talking about matters not only in how big but also in direction, then chances are that should be represented by a vector quantity. So, for instance, when someone says they apply a force to a person, it matters not only how big the force is, but in which direction. So, for instance, if you put a 10-pound force on me, and that force happened to point downward while I'm sitting in a chair and you put it on my lap, then that wouldn't be a big deal because, 10 pounds is not that heavy and I'm sitting in a chair. And even though I'm a rather heavy dude, adding another 10 pounds is not normally enough to break the chair. So it doesn't really matter too much. And the direction's sort of irrelevant. But if you consider now that 10 pounds applied to the top of my head, horizontal to the ground, then all of a sudden you might say, okay, well, that's going to make his neck whip back or maybe make him flip over in his chair or something. That's what starts to make you think, oh, maybe force is a quantity that we should represent with a vector. So that's sort of the guidelines. But we've already learned specifically some examples of what vectors are, and we've learned from this example of walking out your front door how to go about adding them. So I'm going to generalize that to adding vectors graphically. How do we add vectors graphically? Okay, so I'm going to start off with two vectors and I'm going to put them head to tail. So I will say this is vector A. And then right at the head of vector A, I'm going to put vector B. So here is vector B. And when I say adding vectors graphically, I mean if you draw them, you can then draw the solution, and then you can use whatever scale and protractor you use to define those vectors. You can use that scale and protractor to define the solution, and then know or the answer to the addition problem as follows. So what I have here is a vector A, and then at the head of vector A, I put the tail of vector B, and then at the head of vector B, you'll find that that is ultimately the final spot. So if you imagined I followed a displacement from this dot to this dot, then that would be displacement A. And then if I followed from this dot to this dot, then I would have carried out displacement B. And my total displacement from A to B would actually be the vector drawn from the initial tail to the final head, and this would be the vector R, which we call it that because it's called the resultant, resultant. And that's what you get when you add any number of vectors. If I ask you for the resultant of vectors A, B, and C, what I mean is calculate A plus B plus C equals R. So in this case, R is equal to A plus B. So our result that we just learned here is if two vectors are put in head to tail. Oops, I knew that was going to happen. I don't even know why I tried to write it in there. So let me see. If two vectors are put in head to tail configuration, then the resultant or sum is the vector drawn from the tail of the first vector to the head of the second vector. Now you might think, well, Mr. Younger, what if you give me two vectors like these shown here and I have no idea which is the first and which is the second? And you really don't. I mean, just because I called them A and B doesn't necessarily mean that A came before B because I'm not, held to restrictions of the alphabet. What would that matter, right? Well, it turns out that in fact, you can do A plus B or you can do B plus A, and they're both the same. It doesn't matter because, like I told you, those fundamental rules that we learned about arithmetic and algebra in pre-algebra, like A plus B equals B plus A, because this is under that special criteria of a vector space, which is the criteria of an algebra, we know that those rules still apply. So A plus B is equal to B plus A. Now, how do we see that? Okay. Does everybody understand what I've drawn here? And I'm sorry that purple vector came out so shaky. I don't know if I've got Parkinson's or if I don't know. This was happening on last night too. All my vectors were little squiggly lines. I don't know why that happened, but anyways, they're not supposed to be squiggly lines. They're supposed to be straight. But what I want to remind you is when we define a vector, we know that the vector has to have a magnitude and direction. And since that's the only really criteria that we need to implement, because I told you that's equivalent to it transforming like it's supposed to, since that's the only case, then all we need to know is that, oh, I guess as long as I don't change the magnitude or the direction of the vector, I can do anything I want to it. And that's true because right now we're learning about vectors in space. We're not learning about what we'll learn about later, which is called a vector field, where every point in space has assigned to it a very special vector. That's something different. We're not doing that. We're just talking about vectors in space as individual entities. And as long as if you want to move a vector around, you're allowed to do that as long as you don't stretch it, which would increase its magnitude, compress it, which would decrease its magnitude, or rotate it, which would change its direction. So as long as you don't do any of that stretching, compressing, or rotating, then you're allowed to move vectors around all you want. So now, if we look at those same two vectors, let me show you what we can get from that. This first vector A, I went over 4 and up 1, so I'm going to try to do an exact representation of that. Let's say I'm going to use the same color again. So I'm going to go over 4 and up 1. So 1, 2, 3, 4, up 1. So that's my vector A, like that. Okay, and now vector B, I went up 1, 2, 3, 4 squares, and I went to the right 1 square. So that means I should go from this dot to 1, 2, 3, 4, and then over 1. So that means my B vector should be the vector from here to here. And I know that's not supposed to be curved, but again, that's just what we're getting. Let's try it and see if I can do it with this straight thing a little better. There we go. So that is vector B right there. I don't know why that popped up, but anyways, that's my vector B right there. So as I told you, we can do anything to a vector we want as long as we're talking about vectors, not vector fields, as long as we don't change the direction or the magnitude. So what I'm going to do is imagine as if this vector B has a little loop around the bottom, and then that allows me to slide along vector A. So in doing that, I can imagine, for instance, that vector B just slides along vector A. And I'm drawing these series of lines specifically so I can try to stay perfectly parallel to B. There's probably some chance that I didn't get it. But now what I can do is I realize that it's supposed to go over 1 and up 4. So the actual answer should be roughly here. So I'll draw this other version of B in green. And you can see that I did get a little bit off when I was drawing those red lines because I know it's supposed to go up 4 and over to the right 1. So that's why I knew B was. So there's my B. Now we can sort of forget about those red lines, even though those red lines were meant to help us get a better approximation of what is exactly parallel to B. But that's what they were for. Now I'm going to do the same thing with vector A. I'm going to imagine taking parallel to it, parallel to it, parallel to it, and just sliding it along B like that. Now, when I did that, I get A, which again is over 4 and up 1. So there's my A vector. So now what you see is that I could actually move vectors A and B and redraw them somewhere else. And you see that the sum, which went from the tail of the first to the head of the last, that sum is right here. So that's our vector A plus B equals R. So that's R is equal to A plus B. Now you can look at it like, oh, I did take A first because that was the first vector, and I drew my resultant vector from the tail of the first to the head of the last, and B was the last. But if you look instead of looking at the two blue vectors, what if you looked at the green B vector and the blue red vector? Those two vectors are not head to tail, right? Not only that, I could instead maybe just look at the green vectors, B and A. Those are head to tail. And since they're head to tail, we already know how to add them. And in fact, we would draw from the tail of the first, which when I write it as B and then A, the tail of the first appears to be right here, the tail of B. And then the head of the last appears to be right here, the head of A. So I would draw from the tail of the first, which is the tail of B, to the head of the last, which is the head of A. And I would get the resultant is equal to A plus B, which is also equal to B plus A. So now I've shown you that A plus B is the same thing as B plus A. But in so doing, we can again, like I hinted at, we can focus on the B and the A and use that to learn how to add two vectors when they're not head to tail. What if two vectors are tail to tail? How do you add them? So I write that now, and we just figured it out, and maybe you can't put it in words yet, but I'm going to write it in such a way that you will be. If two vectors are put in tail to tail configuration, then we can slide the A vector, or let's say slide the first vector along the second, and then slide, oops, then slide the second along the first to create a parallelogram. So a parallelogram, for instance, notice B and B are parallel to each other, and A are parallel to each other. When opposite sides are parallel, that closed shape called a polygon is what we call a parallelogram. So this, and this is a parallelogram that we just created by sliding B along A and then sliding A along B. Once you've completed the parallelogram, then the resultant is the vector drawn from the common tail to the opposite vertex of the parallelogram. And I could say vertex, but I could also say corner. So what I'm really saying here is notice B and A have a common tail right here, and then the diametrically opposed opposite vertex is where the common heads are. So when I draw the sum, it should be drawn from the common tail to the common head, such that that's the solution. So the vertex of the parallelogram, which I'll also put in parentheses, are to the common head. In other words, when we completed the parallelogram, we had a common tail, which we see was right here where both tails were. But after we completed the parallelogram, we said both heads are over here, so there's a common head as well. So the key thing is that the sum of A plus B when A and B are in tail-to-tail configuration is drawn from the common tail to the common head. Okay, so that's the way you go about adding two vectors if they're head to tail, or two vectors if they're tail to tail. Now, what I'm warning you about here is there will be a question just like this on some test or final exam or something where I will just have two vectors and I'll draw them something like this. Maybe I'll draw vector 1 would be this guy, and then I draw vector 2 would be this guy, and maybe I call that one B and I call that one A, and I would ask you, what is the sum of A plus B? Okay. And what I expect is you to draw right there on those vectors. So this is supposed to be a question on my test. I've got that A vector drawn and that B vector drawn, and it's on your actual test. And I say, draw the sum or draw the resultant of A and B on this diagram. That means it has to be touching this. So let me show you how to go about doing that. I'm going to imagine sliding A along B, and I get something like that. Now I'm going to imagine sliding B along A, and I get something like that. And then I now have completed the parallelogram because this would have been A, and that would have been the head, and this would have been B, and that would have been the head. So this is A plus B. So that's the answer that I expect. If you drew it over here, I'm not going to give you credit. If you drew it over here, I'm not going to give you credit. If you drew it over here, I'm not going to give you credit. Okay? So make sure you understand what I'm saying and you are able to answer these types of questions. I am warning you, this is something that will appear at some point on some test or final exam or something. And if you don't do it correctly, you're not going to get credit. Okay. And it's supposed to be really, really easy. Okay. Let me show you another example. Those two were when they're tail to tail. What if I, for instance, drew a vector like this, called that A, and then I drew a vector like this and called that B, and I said, draw the vector sum or draw the resultant on this diagram. What you then do is draw a vector from the tail of the first to the head of the last, and you'd say that this is A plus B. If you drew it somewhere over here or over here or something like that, you're not going to get credit for it. Okay, it's got to be showing me that you know to draw from the tail of the first to the head of the last, or you know to complete the parallelogram and draw from the common tail to the common head. So that's something that I've seen students repeatedly have problems with. So I want to make sure you guys knew that. That's the way we do it. Anybody have any questions on that? Okay. So what if it's more than one vector? Well, I've already showed you what happens when multiple vectors occur. You just put the first vector down, and then at the head of that first vector, you put the tail of the second vector. And it doesn't matter which one you consider the first, which one you consider the second, which one you consider the third, just long as you include all of them and you put the tail of one on the head of the previous one, and then the tail of the next one on the head of the previous one, and keep doing that. And then when you're all done, you draw from the first tail to the last head, and that will get you the answer. So, for instance, another way you could do it is if you had three vectors and they are all tail to tail, maybe you had this vector and this vector and this vector, and they're all tail to tail. Well, grab any two of them. It doesn't matter which two. And I'm going to grab this one and draw it sliding along there. And now I'm going to draw the leftmost one, and I'm going to imagine sliding it along the one I just drew, and that has allowed me to complete the parallelogram. So if this were vector A and this were vector B, then this would be vector A plus B, and I would call this vector C. Now that I have A and B, then A plus B is represented by that new blue vector, and I need to add to it C. And we learned about the associative property in pre-algebra. Remember, A plus B in parentheses plus C is equal to A plus parentheses B plus C, close parentheses. So it doesn't matter which two you group first. You just group two of them and then add the other one and you'll get the next one. And you can keep doing that for any number. So now that I've evaluated A plus B, I've got a new vector, and now I just need to complete the parallelogram for that one. And that's actually going to be a little hard given the mess I have drawn here. But that's roughly, this is A plus B plus C. So that's actually how you could draw the sum of three vectors if they are all tail to tail to tail. Any questions on that? All right, so I've handled two vectors tail to tail. I've handled two vectors head to tail. And then I told you how you could add any number of vectors head to tail. And I just explained to you how to add any number of vectors tail to tail. So you have all the tools you need. You can actually go further and think about, well, what if they give me two vectors that are head to head? How do I do that? Well, you're allowed to slide those vectors anywhere you want, just as long as you don't change their direction or their magnitude. And you can then therefore slide them so that they're in head-to-head position, or excuse me, instead of being in head-to-head position, they'll be in head-to-tail position, or you could slide them until they're in head-to-tail position. So either one's certainly fine. The main thing is you just know you have that freedom of moving the vectors around. As long as you don't change their magnitude and direction, you can do whatever you want. All right. Now, in order to go on, I need to be able to subtract vectors. I need to know, for instance, what is A minus B and what is B minus A. But before I can do that, I have to introduce the concept of multiplying a scalar times a vector. So if I multiply a scalar times a vector, for starters, I have to let you know that when you multiply a scalar times a vector, it remains a vector. There is some idea. I mean, there's branches of mathematics that if you multiply two different things together, the thing you get is not one of the things you originally had. That actually can be a thing that we have to deal with in mathematics. Luckily, we don't have to do that with vectors. It turns out that as long as we're using these vector spaces, then the parts of it are closed, so that if you do any operation defined within it, you stay within it. So if it's a vector, it stays a vector. If it's a scalar, it stays a scalar. If you take a scalar and multiply it by a vector, that actually does stay a vector. So I'm going to lean again towards my idea of the displacement to help us understand what multiplication by a scalar means. So for instance, let's consider the vector displacement. I'm going to say it's going to go over 2. No, I'm going to say it's going to go over 3, but up 4. So, oops. So this is a vector. and I'll call that vector, no, I'm going to call that vector D for displacement. So let's imagine this is a long walk that you took. You took a long walk out in the open field in Indiana or Illinois or somewhere that's got awfully open, right? Some big farm country in Nebraska or Montana or something like that. So you take a long trip. I think it would make sense if you told someone, "Oh my gosh, walking that trip was really bad, but the next day I did a trip that was twice as long, right?" And in fact, if I went out on the same heading and walked twice as far, then my vector would in fact be over not 3, but over 6 and up not 4 but up 8. 1 2 3 4 5 6 7 8, like that. So now this would be the vector 2D. In other words, if I used a compass in this big open field and one day I walked a mile straight and then just turned around and came back, then my trip would be called the displacement D, right? If the next day I decided to walk the same direction, but I wanted to take twice as long a trip, then I would walk, instead of 1 mile, I'd walk 2 miles, and it would need to be in the same path. And that's the way I go about doing it. So, what we learn is that when I multiply a vector by a scalar, then if that scalar, at least in this case, happens to be positive, if that scalar happens to be positive, it just makes the length of the vector that much longer. So for instance, if you have a vector A and its length is A, then you multiply it by a constant C, the vector c times a will have a length c times a. Okay, so that's the rule. If you double a vector by multiplying it by 2, you don't change its direction at all. You change its magnitude by a factor of 2. If you multiply it by a factor of 1.73, then you change its magnitude by a factor of 1.73. If you multiply its magnitude by 1/2, then you basically make the magnitude of the new one 1/2 of the original magnitude. So in this case, for instance, we would go over 1.5 and up 2. So for instance, I could go over 1.5 and then up 2, and this would be the vector 1/2. Oops. I've got it set up to where it's making my lines better, quote unquote. So that would be the vector 1/2 d. So as long as you're multiplying vectors by scalars, if the scalar is bigger than 1, it's going to make the vector magnitude larger, and the new magnitude will be the scalar times the old magnitude. And if you're multiplying it by a scalar that's smaller than 1, then that same number that you're multiplying it by will be multiplied by the magnitude of the original vector, and that will be the new magnitude. So, for instance, if this first vector, which I think you all know, it has a magnitude of 5, and let me specify that by saying d magnitude. That's the symbol we use for the magnitude of a vector. We either put absolute value bars on it, or sometimes you'll see people write double absolute value bars. Both of those are ways of specifying the magnitude of a vector. Another way is to just write the D without the vector symbol. But either way, the magnitude of D was 5 units. We know that because when I went over 3 and up 4, that's our 3, 4, 5 triangle. So if the magnitude to the right was 3 and the magnitude up was 4, 3 squared is 9, 4 squared is 16, 16 plus 9 is 25, the square root of 25 is 5, so the magnitude of D is 5. The magnitude of 2D, however, is going to be 2 times 5 units, which equals 10 units. Now, if I was doing this in somewhere where it was meters, I'd say meters, but in this case, I'm just using these squares. Similarly, the magnitude of 1/2 d would equal 2.5 units. Okay, so that's what happens when you multiply a vector by a scalar. If the scalar is positive, you're either going to stretch it if the number is bigger than one, or compress it if the number is smaller than one, and the new magnitude will be exactly equal to the scalar times the old magnitude. Now, what I want to do is what about if the scalar is a negative? Well, to argue what that would be, I think you would understand that from pre-algebra, for instance, we learned something about what we called the additive inverse. In other words, every number has to have an additive inverse. That's part of the mythology or the philosophy of this algebra space slash vector space stuff is that each element in there has to have a uh, additive inverse. And the rule for the additive inverse is that A plus the additive inverse of A is equal to zero. With that in mind, and the fact that displacement is a vector drawn from where you were to where you ended up, I think you would all agree that if you walked out on a displacement D and then returned back on that same displacement backwards, the displacement would be zero. So that gives us an idea what negative d would be because d plus negative d must give us the zero vector, which has zero magnitude and an undefined direction. So let's think about that. I'm going to now draw vector d. It's going to go over 3 and up 4. And this is vector d. I'll call this big D because I'm trying to act like it's a different vector altogether. So that's the trip I took, let's say, off my front porch. Now I'm going to come right back home and I'm going to, again, in this case, it doesn't matter whether I took the exact same route or not because I'm talking about displacements, which only capture the endpoints. But the main thing is I want to be able to end up exactly back where I started from where I started. So now I'm going to draw a purple vector that starts at the final spot of D and ends at the initial spot of D. And this one should be, let's call it R for return. Now, if R is the additive inverse, then D plus R has to equal zero because that's the way we define the additive inverse. And we know the additive inverse of R, or excuse me, the additive inverse of D is the opposite. Remember this wording, it's the opposite of D. And that means negative D. So what we see is R is actually equal to negative D. And the only difference between D and R is they're different by an angle of 180 degrees. This allows us, oops, this allows us to conclude that multiplication by -1 makes the direction makes the direction of the vector change by 180 degrees. Okay? So if you just take the head and move it to the tail and take the tail and assume that's now at the head, then you get the negative of d. Everything else is the same. So if I multiply by negative 2d, then I get a vector twice as long as d, but pointing in the opposite direction. So in that case, you might say, going back up to here, if I'll do it below these paragraphs that I just wrote. So now let's say d is going to be over 3 and up 4, like that. So that's going to be d. Then negative 2d is going to be again over 2 and up 4, but in the opposite direction. So I'm going to say over 3 and actually it's going to be over 6 and up 8. 1, 2, 3, 4, 5, 6, 7, 8 right there. So now this vector, actually I got a little sloppy on that last part there. This vector is negative 2d. Notice its length is twice as long, but because of the negative 2, the arrow is pointing down and to the left instead of up and to the right. Anybody have any questions on that? Okay, so that's the philosophy of multiplying a vector by a scalar. Basically, all you do is you're altering the magnitude unless the scalar is negative. If the scalar is negative, then you're altering the magnitude and you're flipping the direction by 180 degrees. That's the only two choices. So you're multiplying by a quantity, a scalar whose magnitude is bigger than one, that's going to make the vector bigger. If the magnitude is less than one, that's going to make the vector smaller. If the sign of the number is negative, it's going to flip the direction. If the sign of the number is positive, it's going to leave the direction alone. Okay. Now that we have that, I can now say, how do we subtract vectors? Now, subtraction is a little different from addition because normally when you subtract numbers, you normally just subtracting one number minus another number. So we don't usually think of subtraction by multiple things, at least with vectors. I mean, you can do it obviously because if you're, for instance, working on your income and trying to figure out, your expenditures or whatever, then you start off with your income and then you subtract from it various bills. That's repeated subtraction. And this still works that way, but you're still really just taking two at a time. You took with the very first bill, you took your total income minus that first bill, you got a new result, and then minus the second bill from that new result would give you another result, and then minus that third bill from your new result would give you a third one, so on and so forth. So you're always sort of treating them as two in a row. That's the main thing here. So I'm going to start off with just like I did before. I'm going to draw two vectors head to tail, and I'm going to try to subtract them. Remember, when we added two vectors head to tail, it was super easy. I just had to draw a vector from the tail of the first to the head of the last. But when I added two vectors that were tail to tail, it was kind of a pain in the butt because I had to complete the parallelogram and then draw from the common tail to the common head. In the subtraction, it's going to be exactly the opposite. The head to tail configuration is going to be a pain, whereas the tail to tail configuration will be a little easier. So let me show you what we mean by that. So first off, I'm going to draw vector A, and I'm going to represent that as a vector that goes over 5, 1, 2, 3, 4, 5, and up 1. So here's vector A. Whoa. And I didn't really like how that turned out. So there's vector A. And then vector B, I'm going to go over 2, no, over 3 and up 4. So I'm going to go over 3 and up 4 would be right about here. That's going to give me this vector right here. That is vector B. Okay, oops, there I'm still in that drawing mode where it's trying to make it nicer. So there's A and B, and I want to say what is A minus B? Well, here's where I'm going to make use of one of those rules. This is the one that you really probably thought was stupid. At least I know I did when I was taking pre-algebra. It's like, duh. But from pre-algebra, we learned that A minus B was defined. Notice I write 3 bars instead of two for equals. Two is equals, 3 bars means defined. So in pre-algebra, we learned that A minus B was the same thing as A plus the opposite of B. Well, like I said, those rules are the same rules that we use for vector algebra. So in that case, that means A vector minus B vector is defined to be A vector plus the opposite of B vector. And of course, the opposite is what we call the additive inverse. This is the opposite of B, which equals the additive, oops, inverse are negative b. In other words, multiplying by -1 is the same thing as getting the additive inverse. So, what we would like to do is find out what the opposite of b is. So, if I wish to do that, all I have to do is put the vector arrow at the opposite end and then draw this vector right next to it. And this purple vector is the opposite of b. But notice when I did that, now the vector opposite b is actually uh, pointing head to head with vector A, and we didn't discuss that, even though I did hint that you could figure out what that was if you wanted. But what I did tell you is you can move any vectors you want. So what I'm going to do is I'm now going to slide that vector B along A. And remember, it basically went over 3 and up 4. So I'm going to go over 3, be 1, 2, 3, and up 4, 1, 2, 3, 4. So that would be right about here. So this is now the vector negative b, which notice negative b and a are head to tail. So we can immediately tell that the sum of a and negative b is this vector. So this vector is a minus b, and I might call that a D for difference. That's not standard, whereas R really is the symbol we use for resultant, and that word resultant is standard, but we might call it that. Notice you could also just complete the parallelogram. We could draw excuse me, let's draw it with the blue. We could draw the A vector over here as well. And that would be fine. So in that case, we did sort of complete the parallelogram, but notice how much more work we had to do when subtracting a minus b if the two vectors were head to tail. I had to reverse b, and then I had to slide b over, and then technically, if you want to complete the parallelogram to make sure you're absolutely correct about the shape, you also had to slide a and all that. So that's how we go about subtracting vector b from vector a. So I'm going to write that to subtract B from A, we have to find negative B and add it to A. So that's the big deal. Now let's do it with two vectors that are tail to tail. So now I'm going to draw vector A. This time I'm going to say it goes over 3 and up 3. So there's vector A. And I'm going to say vector B goes over 5 and up 1, or over 1 and up 5. 1, 2, 3, 4, 5 over 1. So this is vector B. And this time, let's do B minus A instead of A minus B. What is B minus A? Well, B minus A is defined to be B plus the negative or the opposite of A. So what I'm going to do is put the arrow for A at the opposite end of A, and I'm going to represent negative A with this green vector. And now that you see that, you can see negative A and B are actually head to tail, and you immediately know that the sum of these two is drawn from the tail of the first to the head of the last. So this is B minus A. Any questions on that? All right, so just like those last two I showed you, this is something I often do on my test. I'll have two vectors in tail-to-tail formation. I'll have two vectors in head-to-tail formation, and I'll ask you what A minus B is, or I'll ask you what B minus A is, and you have to draw it exactly like I did, attached to it, completing the parallelograms and all that good stuff. Anybody think they're going to have a problem with this? All right. So now that I've done that, you sort of understand the graphical techniques that we could use to actually add and subtract vectors. If you're using a program like AutoCAD, where you can actually draw lines at certain angles of certain lengths automatically, it will always, if you use these graphical techniques and use AutoCAD to draw them, you will get exactly the right answers because AutoCAD does it correctly as long as you make sure you snap the end of your vectors to the ends of your vectors and stuff like that. It will always come out right. So that's a technique you can use if you happen to have access to AutoCAD to check your work on adding vectors. Now I'm going to show you how to add four vectors, and I'm using four because there's four different quadrants, and I want you to understand how in each case, if a vector is in quadrant one or quadrant two or quadrant three or quadrant four, I want you to be able to notice whether it has a positive x component, a negative x component, a positive y component, or a negative y component, and all that good stuff. But I'm going to show you how to add them graphically, and I'm going to show you how to add them algebraically, which is technically speaking, the correct way. Graphically is correct as well, but when you're drawing it, at least with, protractor, straight edge, and a mechanical pencil, and even graph paper, you're going to have some error in it. It's just, inevitable. You'll have some error. But if you're doing it by algebra, as long as you don't make any careless mistakes, you get exactly the right result. So that's what I'm going to show you. But in order to do that, I first got to introduce some vectors, and I got to tell you how we're going to go about creating or listing an actual vector. Because remember, vectors are quantities that have magnitude and direction. So in order to specify one, I have to specify its magnitude and its direction. That's one of the ways we can specify vectors is magnitude and direction. So for instance, we could say vector A is equal to 14.14 newtons at 45 degrees. That is a way of specifying a vector. And when I say just that that ampersand type, it's not an ampersand, but that at symbol, when I do that without anything else to explain the angle, then that means the angle's understood to be in standard position as we learned in trig. And it's measured counterclockwise from the positive x-axis towards the positive y-axis. That's what gives you a positive angle. And specifically in this case, I'm going to treat this as if it has 4 sig figs. So I'm going to say it's 45.00 degrees. Okay. That's one way we could do it. Another vector we could do, for instance, is B is equal to 20.00 newtons. And this one's going to be at 30.00 degrees south of east. So that's what I'm saying here as a new type of direction. I'm saying it's south of east by 30 degrees. So you normally would treat the positive x-axis as the east direction. And then when I say 30 degrees south of east, that means you rotate it downward towards the south 30 degrees from due east. And that would be what we normally call in trig negative 30 degrees in standard formation. Remember, when you measure counterclockwise from the positive x-axis towards the positive y-axis, you get a positive angle like the 45 we did on vector A. But if you measure it clockwise, then you get a negative angle. So this could also be called 20.00 newtons at negative 30 degrees. So that's another way of doing it. There's a third vector I can introduce as well. These are the vectors I'm going to be adding in a few minutes. And vector C is going to be 25.00 newtons. And this time it's going to be at 53.13 degrees W of N, that's west of north. So normally we call the positive x-axis the north direction, and west of north would mean move it to the left of north towards the negative x-axis from the positive y-axis by 53.13 degrees, and that's what we mean by this one. Okay. And then finally, vector D, this is the vector we're going to actually add as well. This one's going to be 40.00 newtons, and this one's going to be at a compass heading. And I'm not going to take the time to write compass heading. I'm just going to write compass head 240, oh, actually 240.00 degrees, like that. Okay, so how do we do that? Well, let me explain all of these by drawing a little coordinate system down here at the bottom. And this is the way your coordinates are supposed to work in physics. This up axis is the positive y-axis, but that's also going to correspond to north, and that's also going to correspond to a compass heading of 0 degrees. So notice I wrote CH, that means compass heading. There's a dot after the C and a dot after the H, plus I'm using an abbreviation. The positive x-axis is going to be labeled with X, but that also corresponds to east, and that also corresponds to a compass heading of 90 degrees. The negative x-axis is pointing due south, and that corresponds to a compass heading of 180 degrees. And then the negative x-axis corresponds to west, and that also corresponds to a compass heading of 270 degrees. By the way, north is also 360 degrees. That comes in handy, for instance, when you have to subtract 180 from something. You can always, go up by 180, or if you go beyond 360, you'll get a larger number and then subtract 180 from that, and it might make it a little easier. But that's the key to understanding all of this. Uh, if I wrote, for instance, a vector right here, and I said this is 15 degrees, then that is at 15 degrees, which means the standard position, but it also means it's at 15 degrees north of east, and it also means it's at 75 degree, actually at compass heading of 75 degrees. So that's all what that one angle means there. If, on the other hand, I had a vector like this, and let's say this is 40 degrees, then this one could represent negative 40 degrees in standard position. It's also 40 degrees south of east, and it's also 50. Actually, I should put an at in front of that anyways, though, so let me go ahead and do that. So at 40 degrees south of east, but it would also be at 50 degrees east of south. This is 20 degrees, so this one could be at 110 degrees in standard position because it's 90 plus 20 is 110, but it could also be at 20 degrees west of north, but it could also be at compass heading of 340. Okay. So hopefully all that gives you enough to follow my thought processes here. But let's go ahead and now do the vector addition with these vectors. So what I'm going to do is rather than have to copy them again, or write them again, I'm going to copy this using a technique that my program allows me to do. I'm going to say copy. I'm going to go to the next page. I'm going to say paste. And we'll put them right here. And that word same was not supposed to be over there, so I'll just erase that real quick. But those are my vectors. These are not supposed to be here either. And those are the ones I'm going to try to add. Now, in order to add them, I'm going to be first adding them graphically, and then I'm going to one by one figure out the x and y components because that's the way you add vectors algebraically is you decompose them into components, an x component, a y component. If it's in three dimension, it would be a x component, a y component, and a z component. We're mostly going to stick with two components because three components is really hard to draw. Normally, if you're working in three dimensions, it might just be best to be doing everything by computer anyways. So you just need to understand how it's done, whether you're using a computer or not, and two dimensions is more than enough to deal with that. So with that in mind, I'm going to start off by drawing a coordinate system. And my coordinate system is going to have a y-axis that points up like so. And it's going to have an x-axis that points horizontally like that. As we said, this is going to be y. Oops. Got to take it off this automatic draw thing. This is going to be the y-axis. It's also going to be the north direction, and it's also going to be the compass heading of 0 degrees. This one's going to be x, but it's also going to be east, and it's also going to be 90 degrees compass heading. And, of course, the rest of that as well. Now, I first want to draw the vector A, and in order to draw the vector A, I have to decide on a scale. This can sometimes take a lot of work, but I happen to have done exactly these problems last night in my class, so you can look on there again. So what I'm choosing for my scale is the following. Scale, 1 Newton is equal to 2 millimeters. That's the scale. First off, I'm going to do is the vector A, which is 14.14 newtons at 45 degrees. Now, because this is on graph paper, the 45 degrees is automatically hit if I just hit the corners of each of the squares starting from a corner. So that's what I'm going to do here. I'm going to attempt to hit it, but it's really problematic on my iPad because my iPad surface is so slippery and my plastic ruler is so slippery. But that looks like it did pretty good. Notice I drew it way longer than necessary because I needed to make sure it actually hit my protractor at the 45 degrees. And you're drawing it from that little circle. That little circle was at the origin of the coordinate system. And then I'd make a mark right up here at 45 degrees. And that has to be that far away from here all the way to here is how far away that line has to be drawn. And then I just draw a line through it, and then I use my ruler to erase it so that it's the proper length. So using my ruler, I'm going to go to 28.28, which is about 28.3, and that means that this vector should end up right about here. So with that in mind, that's how long that vector should be. And that vector is going to represent vector A. And I'll just put it right here. Now, I need to put another vector at the head of that one because that's the way we add. See how my vector got wavy, by the way? Again, sorry about that. But anyways, the way we draw the vectors when we're adding them is we put them head to tail, head to tail, head to tail, but we can really go in any order. Last time I learned this order was a little problematic because I did B and then I did C, and B and C almost erased each other. It was a little bit of a pain. It actually turned out really good. I got low percent error, but this time I think I'm going to do C first, and then I'm going to do B. So, or maybe then I'll do C, D, something like that. So I'm going to go ahead and take this as vector A. So I'll just put an A there, and that's 45 degrees. Okay. Notice 45 degrees is measured counterclockwise from the positive x-axis towards the positive y-axis. That's why it just set at 45 degrees. Now I'm going to imagine a little coordinate system right at the end here. There's my x-axis, there's my y-axis. And at that, I need to consider what 53.13 degrees west of north is. So I'm going to take the hole in my protractor, this little hole right here, and I'm going to put it right at the origin of that blue coordinate system, which happens to be at the head of that vector A. And I'm going to turn it up this way so that I can measure 53.13 degrees from straight up to the west. So that's what I'm going to do here. I lay the protractor on there. I make sure that the center of the circle, it's got little black lines that all point towards the center of the circular hole. I'm going to make sure those black lines all converge on the tip of my vector, which they are doing. And now I'm going to make sure that the 0 degree and the 180 degree are in fact running parallel to the vertical lines because that's what due north is. And I am doing that. Now I'm going to go to 53.13, which would be just barely over 53 degrees. So I'm going to say that should be roughly, oops, might help if I'm not on eraser. I was on eraser, so that's not very helpful. Now I'm going to, oh, I moved my protractor a little bit. Got to make sure this is all working right again. The 180 and the 0 are lined up with the vertical lines. The circle's lined up with the head of the vector, and 53.13 would be right about here. So now I'm going to draw a line from the head of the first vector through that dot, and then I'll use my scale to dictate how long that should be. This is supposed to be vector C, 53.1 degrees west of north, excuse me. And that's supposed to be 25. 2 times 25 is 50. So I'm now going to measure out 50 millimeters. And that 50 millimeters should be the length of this vector. So I'm putting the 50 right on the head of the last vector. And I'm putting the 0 I'm going to make a mark at the 0, and that should give me the right size vector. Actually, it's that second line. So now I'm going to take my eraser and erase everything up to that mark. So now I have vector C. Okay. And you see it's 53.13 degrees west of north, so you have some understanding of what that is. Now what I'm going to do is D, which is supposed to be at a compass heading of 240, 240 degrees. I don't know that I can fit that, so I don't think I want to, because 40 is going to have to require me to go 80. And yeah, I may or may not be able to reach that. I'm going to draw the axes first, the coordinate system first, and then see how well I can measure 240 for this particular one. Now I'm just drawing, I'm eyeing where that coordinate system would be, so you'll have some idea, but I'm actually sticking to the drawing originally. So like my origin on that coordinate is not exactly at the end of vector A. I'm really using the end of vector A, not that coordinate. So in fact, and I don't want to do that because when I change the scale, if I don't change it to the maximum, then the whole scale changes and everything could get jacked up. Speaking of which, I need to check this again. That's supposed to be right. So let's check that. The last one was what, 25, so that was supposed to be 50. If I scaled it right, this should still be 50. I just want to double check it since I accidentally changed the scale. No, it's right on the money, so I'm good with this. Now, if I do 240, that's going to be 30 degrees below the horizontal left axis. So that would be along this angle right here. And now I got to see if 80 centimeters or 80 millimeters would actually fit there. And no, it does not. So I do not want to draw that vector yet. I'm going to attempt to draw vector B next instead. So vector B is 30 degrees south of east. So I will do that. I'm going to take my protractor. I'm going to put the center of my circle at the end of that vector. Notice the curve is down because I need to measure 30 degrees south of east. So I need to measure 30 degrees down this way, and this would be east. So in doing that, I'm checking to make sure everything is horizontal. That's supposed to be horizontal, and everything that's vertical is vertical. And 30 degrees would be right here. I just made a dot uh, where that's supposed to go, and it's the left end of that mark. Now I'm going to draw from the tail of, or the head of that previous vector through that little dot. This vector I'm going to make red just because I haven't used that color yet. All right, turn it. My arrow slipped. I mean, my ruler slipped. That's the problem with this. It's so slippery on the surface. That's pretty close. I missed it by a little bit, but I'm not too terribly worried about it. Now, this one's B, so that's supposed to be 20 newtons times 2, which would be 40 newtons to get it to scale. So it should be 40 millimeters. I said 40 newtons. Sorry about that. It's supposed to be 40 millimeters. And yeah, I just scaled it again. Let's check the 50. That is not good. That is not good either. Such a hassle to try to do this. There should be a default scale that we could always go back to, but I haven't found any such thing within my program, so I'm not sure if such a commodity exists or such a setting exists. Okay, now I'm back where I'm supposed to be, so that should be the right scale. Now this one's supposed to be 40, so that looks like it's going to end. My finger stops pushing things. That would be super helpful. That's supposed to end right about here. So now I can take the vector and say that its end is right here, and this vector is vector B. And what we're seeing is this angle right here is 30.0 degrees, and that's where vector B is. Now I just need to put vector C at the end of that one. So I'm going to draw another coordinate system right here and here. Okay, and this time I have to draw 53, or excuse me, I have to draw D, which is 240 degrees. That should be 30 degrees south of west, is another way of looking at that. So I'm again putting the center, the circle of the protractor at the head of the red vector, and I'm holding it like this so that I can measure down 30 degrees from west. Man, I hate it when it keeps scaling like this. So I can do the angle. The angle won't be bothered by the scale. I'll fix the scale again in a second. But right now I've got this and I need to do 40 degrees, excuse me, 30 degrees downward. That's going to be right here. Now I'm going to make sure this thing's scaled again at 50 so that my blue vector is still 50. It's not. So I got to change again, change again. That's too much. Still just a little too big. Hopefully I didn't go too far that time. I did. Of course I did. That's really close, so I'm going to go with that. Now I've got to draw the 80 millimeter because 40 times 2 is 80. So now I've got to draw the 80 millimeter, and the 80 millimeter is going to start at the head of the vector, the red vector, and it's going to go through that little black dot there. And hopefully, and this time I'll use green because I haven't used that yet. It's supposed to go roughly that long. Let's check and see if that still looks like 80. Yeah, the 80 is roughly here. So that should be the approximate end of that last vector. This is vector, that last one I did with C. So this one's D, and this is 30 degrees, and that's vector D. Now, I've got all these vectors. I put them in any order. It doesn't really matter, but I put them in the order A plus C plus B plus D. And now the resultant starts at the tail of the first, which is the origin, and ends at the head of the last, which is the end of vector D. So what that means is our final vector, which I'm going to write as purple, our resultant vector is going to be this one that I draw from the origin to the tip of that green arrow. So that is supposed to be our resultant vector. And I can tell from this protractor that the angle that that is down by is approximately, let me measure it real quick because my protractor is not really small enough to get that. This looks like it's going to be right on the money for 12.9 degrees. And the length of it, the magnitude of R, I'm going to measure this in millimeters and then divide by 2, and that'll give me newtons. And I measure it, and it appears to be 55.9 maybe. And 55.9, when I divide that by 2, that'd be 25 plus 2.5, that'd be 27.5 plus 0.45, 27.9. So this would be about 27.9 newtons. Actually, let me check that math. I want to go ahead and carry an extra decimal. So 55.9 divided by 2 gives me 27.95. So I'm going to call this 27.95 newtons. And really, we shouldn't be necessarily using that fourth digit because it looks like most of the stuff we only got 3 digits on the work, but that's okay. We're in a good spot now. We should be able, and I don't know what happened with this stuff that came in here. This is just some magic that happened for whatever reason. Must have been I hit a button or something. But either way, I now have this. I don't know what the scale is currently on because it changed, but luckily it changed after I made the measurement. So hopefully this will still work pretty well. Now I got to show you how I do this algebraically. We've already figured out the results graphically. The results graphically is R is 27, we probably call it 28.0 newtons at 12.9 degrees south of west. That would be our resultant vector. Now I'm going to show you how to add it algebraically. I'm going to first take vector A and I'm going to draw it up here in the top right. And I'm just going to draw a representation of it, even though it's not exactly accurate. I'm going to try to draw it like this. This magnitude of vector A was 14.14 newtons. This was at 45 degrees. And what we do is we can imagine the shadow cast by this. If you picture that black vector as if it's a sheet of plywood leaning against a building, then the sun being directly overhead would create a shadow directly below it, and that shadow directly below it is what we call the x component of that vector, and it happens to point in the positive x direction, so that's a positive x component. Similarly, if we imagine the shadow cast by a horizontal light pointing to the right, we would see that this is the positive y component. So this would be, since I've drawn these as vectors with arrows on them, then this would be a sub y with a vector symbol, and this would be a sub x with a vector symbol. And using my trig functions, which I use, some old horse came a hopping through our alley, but many people use SOHCAHTOA. Any of those are fine. The main thing is when I look at the sine of theta, the sine of 45.00 degrees, that's supposed to be opposite over hypotenuse. And the angle opposite the 45 is or excuse me, the side opposite the 45 is a sub y. And then the hypotenuse, if you draw on the right triangle, the little right angle, that little right angle looks like an arrowhead and it points towards the hypotenuse. So you see that the hypotenuse is in fact 14.14. So I say a sub y is equal to positive. Now I forced that positive in there because I saw it pointed up. You have to do this with every time, with every component in each quadrant. You have to look and say, okay, do I have to, in order to get from the tail of the vector I'm decomposing to the head, do I have to go right or left? If I have to go right, then it's going to be a positive x component. If I have to go left, it's going to be a negative x component. If I then have to go up, it's going to be a positive y component. If I then have to go down, it's going to be a negative y component. So you've got to force that symbol. And in this case, I'm going to take 14.14 times the sine of 45, and that's going to give me, it says 9.998, which I'm going to call positive 10 because that's darn close to positive 10. So that's 10.00 newtons. Similarly, the cosine of 45 degrees is equal to adjacent over hypotenuse. Remember, I did have 4 sig figs, so that's why I'm reporting 4 sig figs. But adjacent side is the side that touches the angle. The opposite side is the side that doesn't touch the angle and is not the hypotenuse. So in this case, cosine 45 is equal to a sub x over the hypotenuse, which is 14.14. So A sub x in this case is also positive, and it turns out to be 14.14 newtons times the cosine of 45, which again gives me 10.00 newtons. So that's how I figured out the x and y components of vector A. That is something called decomposing a vector, and you should always be able to do that. Now I'm going to do vector B. Again, I'm not trying to draw it to scale, but I am trying to get an idea of roughly direction and stuff like that. So this is our vector B. It had a magnitude, actually, the blue one was vector C. Sorry about that. It has a magnitude of 25.00, and that angle is in fact 53.13 degrees. That's not big enough for you guys to analyze, so I'm going to redraw it. And obviously, I'm not doing it very well to scale because this angle is less than 45 degrees when it's supposed to be 53.13, but that's okay. This is the 25.00 newtons. If I draw the right angle, I can see the 25.00 newtons is the hypotenuse. I can also see that the y component is positive. So I'm going to draw that green. And this is, of course, C sub y. And the x component is negative, so I'm going to draw that red. So this is C sub x. And now I'm going to compute that the sine of 53.13 degrees is equal to opposite over hypotenuse, which in this case, the opposite is C sub x, but the hypotenuse is 25.00 newtons. And I also say that cosine of 53.13 degrees is equal to adjacent over hypotenuse, so that would be cy over 25.00 newtons. So that tells me that cx is actually negative, and I'm going to multiply 25 times the sine of 53.13, and that gives me 20, negative 20.00 newtons. And C sub y is a positive quantity. Again, I'm forcing the positive sign here. That's key. You've got to understand that you got to force the sign. And in this case, I'm going to take 25 and multiply it by the sine of, oops, I did sine last time and I was supposed to do cosine. So I'm going to write the 20 down here because I actually used the wrong function. And I'm going to erase that 20 up there. Sorry about that. Now the C sub x is supposed to be 25 times the sine of 53.13. Oop, wait a second, I did do that right. 25 times the sine of 53.13 was supposed to be C sub x. Oh yeah, so that's fine. Sorry about that. I just typed it in myself the second time wrong. The first time it was correct, so I didn't need to correct that. Now the C sub y is going to be 25 times the cosine of 53.13. 25 times the cosine of 53.13 is 15. So I get 15.00 newtons positive. That's my x component or my y component of C. Now I'm going to do vector B, which really should be a fourth quadrant thing. Uh, so because of that, I'm going to do that one in the fourth quadrant. So I'll draw it right here. And this angle right here is 30 degrees. This magnitude for vector B was supposed to be 20.00 newtons. And we can see that the x component goes to the right, which is positive. The y component goes down, which is negative. So I'm going to say red for the x component. And then I'm going to say green for the y component. Oops, I meant to do that the other way around. I'm going to do green for the x component because that's positive, and then I'm going to do red for the y component because that's negative. So this one should be b sub y, and this one should be b sub x. And now the calculation of the trig gives us that sine of 30.00 degrees is opposite over hypotenuse, and that is clearly by over 20.00 newtons, and that gives me by, which is negative, is equal to 20 times the sine, times the sine of 30, and that gives me 10. So this is negative 10.00 newtons. Similarly, the cosine of 30.00 degrees is equal to adjacent, which is b sub x, over hypotenuse, which is 20.00 newtons. So that tells me b sub x, which is positive. Again, I'm forcing the sign. That's going to be 20 times cosine 30 degrees, and that gives me 17.32. So now I've got the three vectors all broken down into components. All I have left now is the green d vector, and the green d vector seems to be 30.00 degrees from horizontal to the left, and this has a magnitude of, this green vector was the 40 newtons. And I can see the x and y components are both negative, so the x component is going to be red, and the y component is also going to be red. So this one is, in fact, d sub y, and this one's d sub x. And now I can take the sine of 30 degrees is equal to opposite over hypotenuse, so that's dy over 40.00 newtons. So that gives me dy is equal to a negative. Now I'm going to say 40 times the sine of 30, and that gives me negative 20.00 newtons. And then cosine of 30.00 degrees is equal to adjacent over hypotenuse. So that's dx over 40.00 newtons, but it's also negative. So dx is equal to negative 40 times cosine 30, which is going to give me 34.64 newtons. So now all we have to do is combine like terms. This is why we break down the vectors or decompose the vectors into x and y components. The sum of all the x components is the x component of the resultant. The sum of all the y components is the y component of the resultant, so that we have this nice little formula. R sub x is equal to a sub x plus b sub x plus c sub x plus d sub x, which in this case, I can go around and add them. I see a sub x is 10, and then b sub x is 17.32, so I say 10 plus 17.32, and then c sub x is negative 20, so I say minus 20, and then d sub x is minus 34.64. So 10 plus 17.32 minus 20 minus 34.64 is negative 27.32. So that's the x component of my resultant. The y component of my resultant is a sub y plus b sub y plus c sub y plus d sub y, which in this case is going to be a sub y is 10, b sub y is negative 10, so 10 minus 10, and c sub y is plus 15, so plus 15, And then d sub y is negative 20, so I'll say minus 20. So I did 10 minus 10 plus 15 minus 20, and that gives me negative 5.00 newtons. So now I have the x and y components of the resultant, and I'm going to copy this to the next page and show you how to build a vector from components. So what we just did with those four vectors was we decomposed each of them in their x and y components. Now we're going to construct a vector out of its x and y components. I'm going to paste this right up here so we have access to it. And now I'm going to draw my coordinate system and then redraw this resultant vector right here. There's my x-axis. There's my y-axis. My x component is 27.32 in the negative direction. So I'm going to say roughly this far. And then my y component is negative 5. So I'm going to say maybe this far. So this one is 5.00 newtons negative, and this is negative 27.32 newtons. And in fact, the resultant is this green vector right here, r, and this angle I'll call phi. So according to trigonometry, the tangent of phi is equal to opposite over adjacent. That would be 5.00 newtons over 27.32 newtons. Notice I didn't include the signs. Do not include the signs, and also do not take trig functions of angles bigger than 90 degrees. You can do that, but it just leads to a lot of problems unless you know your details of, what's positive and what's negative in the first quadrant, what's positive and negative in the second, what's positive and negative in the third, what's positive and negative in the fourth. It's best to just choose the angle that's closest, that is between the vector and the closest axis, and use an angle that's less than 90, and never put in the signs and all that good stuff. But now that we have that, I can say that phi is equal to the inverse tangent of 5 over 27.32. We technically had 3 sig figs and 4 sig figs. Division would make it down to 3 sig figs because it's 5.00. So if I take the inverse tangent of 5 divided by 27.32, I get 10.37 degrees. And that seven's an extra digit that's not a significant figure. So we had estimated the angle was about 12.9 when in reality it's more like 10.37. Now the magnitude of r is just given by the Pythagorean theorem. So r squared is equal to r sub x squared plus r sub y squared, so that r is equal to the square root of 27.32 newtons. That is technically negative, but when you square it, it's not going to matter anyways. And similarly, the r sub y is negative 5, but again, when you square that, it's not going to matter anyways. So 27.32 squared, which has 4 sig figs, gives me 764.4, and then 5 squared gives me 25, and then I add 25 plus 760 or 746, excuse me, 0.4, and that gives me 771.4 newton squared under the square root, and I take the square root of that, and that gives me 27.77 newtons. So R, our resultant vector, should be 27.77 newtons at, in this case, I'm going to say 10.37 degrees south of west, but I could also call it 27.77 newtons at 10.37 degrees No, actually, I wouldn't say 37 degrees. I'd say 270 minus 10.37 would give me instead compass heading of 259.6 degrees. That's another way of writing it. And there's several other ways, but that's one way. And then the other way is, and this is what I'm introducing now, one of the things you're supposed to learn in this course is that one way we can specify vectors is defining a unit vector that points in the positive x direction as I hat, and then a unit vector that points in the positive y direction as j hat, and then a unit vector that points in the positive z direction as k hat. Then this becomes uh, negative 27.32 newtons I hat minus 5.00 newtons J hat. But in case you forget the I, the J, and the K, there's also a way where you can write it as negative 27.32 newtons X hat minus 5.00 newtons Y hat. That's acceptable as well. And then there's a shorter way you can write it where you use less than symbols, just like we do parentheses to find points in a coordinate system. We can use less than symbols to find components in a vector. So in this case, it'd be 27.32 newtons, negative 5.00 newtons, and zero point 0.0 newtons, meaning if we had a z component, it would be zero. But we can also just use two of those, and everybody will understand that it's 27.32 newtons in the x direction and negative 5.00 newtons in the y direction. All those are equally accessible. Notice my percent difference. I got 27.95 graphically, so 27.95 minus 27.77. That is a difference of 0.18, and now I divide that by the accepted value, which is 27.95, and I move the decimal two places to the right, and that gives me that the magnitude is only off by about 0.6% is percent error of the magnitude of R. So doing it graphically, I got less than 1% error for the magnitude. For the direction, it would be 10.37 minus 12.9 divided by 10.37 and then times 100 to make it into a percent. That would, of course, be that's around 24% error, but that's because the angle's so small. Is percent error of the direction. So that's it. I've now taught you what you need to know about how to add vectors. The class is over. You guys are free to go. I'll wait for the last person to leave in case anybody has any questions. And I will see you all next time. So does anybody have any questions? I'm just going to wait for the last person to leave and see if
Hey,
anybody has any. Yes.
it's Shania again. You told me
Yes.
to talk to you after class.
Yes. Yeah, I just meant, but I'll send you a text or something like that. But we can also do it here if you need. That's not a problem.
Oh no, you can send me a text. That works too. Whichever way works best for
Okay.
you.
Did you already text me or did you just send me emails?
I would just send you emails. How can I find your? Because I told you. Remember, I sent you an email saying I didn't know how to use Canvas and stuff.
Yeah, I remember
So
that.
yeah, that was very helpful the way you sent it back. I was able to find out how to get to Zoom today for me so I can join one of the class, join first class, on my first class.
Good deal. No
But
problem.
so I don't. Where is your number in the syllabus?
I just typed it in the chat. So that's my phone number. If you send me a text message with that, I'll reply to you and we'll discuss it that way.
Okay, that would be great. Let me get it from the chat.
No problem.
Thank you.
No problem. And I'll be communicating. It'll probably take me about 20 minutes before I can address it, but I'll be there in about 20 minutes or so.
Okay, thank
You're welcome. How about you, Alexander? You have any questions?
Hey, yeah, I just wanted to confirm some things about the first test. Is
Hmm.
it only I was looking on Canvas and I couldn't really find much. It's only going to be on chapters 1 and 2, right?
That's correct.
And then when will we know, like is it a for sure decided thing that we're going to be taking the face-to-face person on Thursday?
No, no. So your class, you're in this class, NO2B 241, correct?
Yeah, I'm in this class.
Okay.
I was a little confused. Is there what a lot of the normal people in this class weren't here today. Is that for a reason?
No, actually, I was surprised at how many people were here, to be honest with you. But there was a lot of people that were from other classes too. A lot of people just don't show up because I'm not really strict about showing up, and I put the videos online, so some people find it just as comforting to watch the videos later. And I've also discovered that some students never even watch the videos. I don't know how they survive without watching the videos, but some people do that, so that could be the problem. Now, in general, during the summer. We have 3 days off from lab that we reserved for testing times, but because I messed up some stuff in putting up the syllabus dates, I made it where I didn't think it was fair to give you all the tests on this week, which would have been, I think Thursday is what Dr. Johnson would have had you take it,
Yeah,
which would be
because
tomorrow.
we actually don't have a lab on Thursday with
Oh,
Mr.
okay.
Johnson.
This
Yeah.
week or in general?
No, just this week
Okay,
he
yeah.
sent out an email that there wasn't going to be a lab this Thursday.
Yeah, yeah, that's I sent him a lab that's in communication with me, and I told him he could do anything with that he wanted, which could be just nothing. What I would tell you guys to do is use that time. You're supposed to be in there for like 3 hours. Use that time to take the practice test at least like 3 or 4 times.
Yeah.
That way, you're getting your money's worth of the instructional time, but you're getting it from the testing, the practice test, as opposed from the instructor. But you're also able to text me and email me if you have any questions on it. Just take photographs of the questions that are bothering you with the answers and ask me them. But normally that's how the test will go. But in this case, I just made it a online test that you're going to do with Respondus Lockdown Browser and Respondus Monitor, and it's going to be online. It's going to have some parts that'll be multiple choice, maybe, but in general, they're going to be free response questions where you're going to work out the problem and show me your work and then turn in. As far as the computer goes, where you're typing in the answer, you're just going to type in the answer, period. If you can put the units, that'd be great, but at least make sure the units are in the work that you're going to write on paper, because what's going to happen is at the end of the testing time where you're typing in your answer for each question, you will take each of your pages that you have that includes your equation sheets and all the work paper that you did, all the scratch paper, and you're going to slowly show me the camera them one by one so I can see every square inch front and back of every page. And then you're going to submit the test, and then you're going to have like 15 minutes to email me or text message me. I prefer email, by the way, in this case. Text messages
Okay.
take too much of my bandwidth. But email me a PDF of those solutions that you wrote out, and then I'm going to grade it like I would a normal test that someone took in my class.
Okay, so we basically we have two online tests just for this first one.
Yes, you have the online one that you're allowed open notes, open book, open uh, internet searches, and that sort of stuff. Then you had the what we call face to face. That one you're not allowed to have anything except the allowed equation sheets and allowed facts that are listed in the important documents and links, and you're just going to work it out with your calculator and paper.
Okay, awesome. And then this was what something you went over first class, but I wasn't sure if it would actually be on it. Like, are we going to have to know how to convert units to like a long extent
Yeah, that's a very realistic problem, but I give you all those constants. If you looked at a hard copy of the textbook, it would have the inside covers that has all these facts in it. That's basically what's in those documents and helpful documents and links. That's what you're going to have access to. You'll also see them at the bottom of the practice test. So when you look at the bottom of the practice test, you'll see equation sheets, but you also see all the facts that are there, like the SI prefixes, the conversion factors from meters to miles to feet and all that stuff. All that's given to you. But yeah, you're absolutely going to have to be able to convert units. And it might be, a long line like I did from miles per hour to meters per second or whatever. It could be like that, but all those constants will be given to you.
Okay, awesome. And just one last thing. So you were saying like you're not really super strict on attendance. Is there like this time doesn't really work super well for me? Like,
Right,
do
yeah.
what is the attendance policy? Like, do I still have like I'm gonna
No,
show up
no.
to most of
If
them, but should I still email you?
Yeah, if you don't show up, just let me know. Like, send me an email and say, hey, this, as we talked, I can't fit this into my schedule that well. I'm probably going to miss, but you can attend Tuesday and Thursday classes, or excuse me, Monday and Wednesday classes, because I do the same thing on Monday and Wednesday as I do on Tuesday and Thursday for your class. So if that helps you, you can attend that one. But either way, I'm not monitoring it and saying, hey, this student didn't show up, so I'm going to drop them. I don't do that with my internet classes. But if I see that you get behind, you miss a test or something like that, then I'm going to start thinking, okay, let me watch their attendance, and I might need to drop them because that's the instructions we get from the powers that be above us.
Okay, well, thank you so much. Have a great day.
No problem. Have a good one, Alex. All right, so I guess that's it. Have a good one.